Welcome to Physical Chemistry. Today I'm interested in how spectrometers work. To make a spectrometer we will need some parts, so let's think about that first of all. So what we want to do is measure light at different wavelengths, the intensity of the light of different wavelengths interacting with something in some way. So we need to split the light up into different colors, and we can do that in the simplest way with a prism, which you would have had in physics. So if we have a beam of light coming in to a prism, it has to come in slightly off center, it will be split into different colors. So the mixed light coming from our source is split into different colors, and we can look at it further away. So let's put prism. But usually in practice we tend not to use a prism. They were used initially in historical devices, but now we will use a diffraction grating, and typically a reflection type of diffraction grating, because they are more efficient in terms of how much light comes back out of them. So if we take a diffraction grating, you will also have heard of those in physics. So let us do that. I'm trying to work out a way of drawing it. Let's draw it from the same side. So let's have a diffraction grating here. And what the diffraction grating is going to do is the same thing, but it does it in a different way. So the prism is bending the light, and it bends the different frequencies of light to a different extent. And if it was a parallel-sided prism, it would bend them back, and they would be back in the same beam, just slightly delayed in time, which doesn't make a lot of difference if it's a continuous beam. If we have two bends in it and they're not quite the same amount, then we get a spectrum coming out. In this case, what we want is a set of reflectors that are little silver or gold or aluminium lines on a mirror with little bits that are dark in between, or let the light straight through. Then we can say the wave coming off this, let's choose a direction over here, the wave coming off this line and the wave coming off this line have a different distance. So this is our starting point. So we have a photon comes out here at this phase. I'm not going to be able to draw this very neatly. So it hits at that point in its wave. Let me try to get this to work. So these two beams hit our surface at different phases in their wave, and they reflect it. Let's try to work out how that's going to go. Reflect it in this direction, and when they get back to the same position, ooh, look at that, it's worked. When they get back to the same position, they are not in phase with each other anymore. That leads to the brightness of this position being different to the brightness of the original beam. And if we choose a different angle to bounce it off, we get a different distance change, particularly if we change the angle on this side, but also if we change the angle just on one side. So if we change both, we get more effect. But if we change just one side, in this case, we might want to look at this here, and we would see a series of spots, bright and dark, over here. This comes from, this is effectively a more efficient and more advanced version of double slit experiment, which you probably have come to in physics. So if we take a double slit experiment and we have a wave This also works with water. You may have seen this in school. It's a really good experiment in school. So we have a wave of water that comes up to it. These are the waves on the water. Sorry about the auto white balance again. So the next one would be just hitting here, and then the one after, which should be here, would be a wave coming out. I've slightly out, but never mind. Let's try to draw those. So let's draw one here, and our waves from here come out, and obviously this is going to go a long way, but I will run out of the ability to draw it neatly very quickly and get confused. However, if we take where the peaks of our wave are lining up, I've missed that one slightly, we get a straight line in this direction. And if we take peak trough, which would be peak trough, that would be here and here. Peak trough, I'm trying to get not a curve. So we would get a dark spot. This is light. And we would get a dark spot over here. I probably shouldn't have drawn the dark spots. It's easier to draw the light ones. We would get a set of bright spots on our, whatever we have, on our camera or our background. Oops, I'm stuck to my table. If this is slits in this vertical direction, then we would get lines in this direction, which is better because it's more efficient. We get more light, it's easier to detect. So the diffraction grating, that's this, uses the same physics to do exactly the same thing. It splits the light into different colors at different angles, just like the two slit experiment. It's a little bit more complicated than that. So we get a spectrum at one angle, we get a normal reflection quite sharp over here, which is nearly every color, not very split, and there are higher orders of reflection further out, just like these spots. But what we're actually doing is we're looking inside one of these spots at small differences between the wavelengths here, which are also split into different colors. Okay, so we kind of started in the middle because this is splitting the light up, but first of all we need to make it, and we also need to detect it. Those are the other two key components inside our spectrometer. So we can think of, so light source, we can think of how we're going to get the light. So the normal way that you might be familiar with, although they're not so common anymore, would be a heated element. So in a normal light bulb, this would be tungsten, and there would be some gas around it. Typically in new bulbs, it would be a halogen. So we would have a small amount of halogen in there and some inert gas. So we might have xenon or something in there, and this would run really hot. So we would have current going through here. It doesn't really matter whether it's AC or DC because it stays hot between the cycles of the AC, so we don't see flickering. But it's better if it's constant. So that would be a light bulb. We could of course use an LED, and those are very bright these days. An LED, do I want to tell you how an LED works? Yes, let's talk about how an LED works. So an LED has effectively an energy level diagram somewhat like this, where there are energy states high up and energy states low down. Let's have the low down ones filled up. So, and we are going to force our so we're going to force electrons in here. It's effectively an insulator. There are no electrons in here, and there are electrons in here. But if we attach it to a power supply, we can force electrons in here, and we can pull electrons out of this side. So we end up with an electron here and a hole down here. We need to use a more complicated semiconductor setup to do that, but that's not important to our actual understanding right now. So I'm hoping the physicists will cover that. And the electron falls down. Let's have just a single electron falls down, so it's got one arm, and it gives out a photon of light when it does it. Because we've attached these to a power supply, we actually bend the energy bands, but in the middle where the light is coming out, it is not bent. And we're looking at the electron joining up to a positron, joining up to a hole, forming nothing, and the energy difference has to go somewhere, and it comes out as a photon. That is a non-coherent but very bright single color light from an LED, unless it's coated. And the advantage of an LED is that we can give a single color out. So if we have a type of spectroscopy which requires a single color, it is a lot cheaper and more effective way of doing it than having a light bulb and cutting out most of the light. Obviously, if we want to go up to the more extreme case, we would need to have a laser, and a laser functions similarly to an LED. We will come to that later, but the laser will give out a very high power light in one color. Depending on the type, it may or may not be coherent. So LEDs are not coherent. A typical laser is coherent, which means all of the light is in step, but for spectroscopy it doesn't usually matter. So we typically will end up with an LED unless we need incredibly bright light of a single wavelength. For infrared, this type of light bulb is fine because it gives out a lot of infrared, but it's a lot more efficient to use a fatter wire, and it's a lot cleaner if we use a piece of silicon. So effectively it's just a bar of silicon with current running through it that gets kind of warm. The third part of our spectrometer would be the detector. And we need to be able to measure the light that's coming in. That becomes more and more difficult if we have less and less energy. So what we had before is a CCD, which would be a charge coupled device from a camera. So in this case we can apply a voltage to our semiconductor much in the same way as before, but instead of it generating electrons and whole pairs and generating photons, it's too low a voltage to be able to do that. So when the light photon comes along, it promotes an electron up into the conduction band, and because it's then going directly into our power supply, we can measure it. Depending on the type of detector, one photon can release more than one electron, and then we can measure a higher current. It is possible to tell the difference between different colors by doing that, but then the light photons would have to be coming along one at a time. That is one type of detector. We'll talk about that later when we get up higher in energy. But at these lower energies, we need to separate the colors of light beforehand in some way, because we get a similar signal from every type of photon. So being able to count the electrons is not very helpful. We also need a lot of photons, a lot of light particles coming in. We need bright H nu. We need a lot of light particles coming in to be able to measure a decent signal compared to the noise, because the problem with low energy light is that the difference in energy between these two levels has to be small, and if it's small, then heat can cause this to happen accidentally. Then we get a basic, so a base signal of noise of just from it, the detector being warm. It helps a lot to cool it down. Even the detectors in normal cameras are way better if they're cooled. The second type of detector would be the photomultiplier, which works by a principle that we will also come on to later when we get higher in energy, because it's more common there. So if we have a vacuum tube, let's have it going this way, and we have a piece of metal on there that's somewhat negatively charged. If we shine a light on it, whoops, let's put it like that, the light can promote a photon, it can promote an electron into the gas phase. So it's a similar process to here, except rather than being a semiconductor, the energy of this conduction band is higher and the electrons can be kicked right out. We need to fight against the work function of the metal, which is quite difficult, so electrons don't just fall out of metals easily. It takes a certain amount of energy, but we can help that by applying a negative voltage, which makes them easier to get out. It's obviously better if this is in a vacuum, otherwise the electrons coming out will hit stuff. And if we have another surface here, which is not quite so negative, so let's have negative, negative, and negative, the electrons can hit this surface, and one electron can knock out more than one electrons on the second surface, and going to another one, and another one, and another one. So typically there would be a cascade of these inside, and the last one will measure, will be positive. The last one will be a positive electrode. It collects all of the electrons from these metal surfaces, and it gets a lot of electrons for one photon, which is why it's called a photomultiplier. So every step we multiply the number of electrons that we are generating. This can be used in a lot of cases, so we can use it in an electron detector because we don't need this first step. So if we want to measure electrons, we use exactly the same technology. So you will come across this quite often. Obviously not in this course because it's more about spectroscopy, but right at the end we'll get up to that energy range. So now let's look at what type of spectroscopy we would like to see. So starting with UV vis, because it's a type of absorbance spectroscopy, we want to see how much light we started with and how much light we end with. So if we have our source, that will be a bulb over here. That will be our source. We need some way of turning it into a point source because a bulb is not a very good point source, so we need a small hole to convert this light into a point source so that we can play with it properly. And then we have a question. We do need to have a prism or a diffraction grating in here to split the light into different colors, but it doesn't necessarily need to be before or after the sample. We only need one. It could be before, could be afterwards. Let us put it before the sample because that means we get less light on our sample the whole time, because the problem with UV is it will tend to damage our sample and it will break it. So we tend to start a spectrum, a UV visible spectrum, we start in the visible region and come back in energy to, or back in wavelength, up in energy to the UV, because then we don't damage the sample while we're trying to measure it quite as much. So this will be our light source. It goes through, there will be some optics to play with it and to fold it around so that it fits inside the spectrometer, but we don't need those for the purposes of our measurement right now. I'm going to put in an element that we will ignore initially. So the light goes through and it gets to a no. Do I want to do that first? Let's split the light up first. Hang on, I'm going to start again. So having improved my diagram, we've got a rotatable diffraction grating here. So our light comes in as a small beam. It hits our rotatable grating. This could be a slit as well, as long as the direction was correct. Then it gets split into different colors. The colors that we don't want right now are blocked by this second aperture. Should have called it an aperture. But hole is what it really is, and aperture just means it's small. So it goes through the first aperture, is cut into a small beam, which hits our grating, is split into different colors, and just one color makes it through the second aperture, which could be a slit as long as the first one is a slit. This grating we can rotate, which changes the angles here, and that makes it allows us to choose which color comes out of here, or it allows our spectrometer to choose which color comes out of here. Now it's going to come along and we are going to bounce it. Let's bounce it off a mirror so that it goes through our sample. So this will be our sample. And typically we want the walls of whatever we're holding our sample in, so it's UV vis, this could be a liquid, the walls that we're holding it in to be perpendicular to the light beam so that it doesn't get bent by that. We don't have to worry quite so much about what these are made of. So it goes through our sample and hits a detector. Let's have a detector here. Detector. So that's one possibility. To make this better, because we have a little bit of a problem, this source can change color over time. Maybe the mirrors are wobbling a little bit, maybe things change, and because we're measuring a very small amount of light, remember we're trying to measure absorption, so we might be trying to measure a very tiny percentage of the light accurately. We typically need to have a reference beam. So now I need another element in here that cuts off half of the light. So this would be a half mirror. Half mirror. That reflects half of the light through an empty reference. Ideally the same as our sample, but without the thing we want to measure, and depending on how good our equipment is, we might have another detector. In our low-grade machine, which is the one we usually use, we have two detectors and two paths. If we take this, just the last part, so from here, take the last part, so ... all the rest of it is the same, and we have a more swanky device, a much more posh one. We would have a mirror that is on a fan, so it's rotating. So half of the time it is a perfect mirror in this direction and goes through the reference, and then it gets reflected into the detector. What's the best way to do this? Yeah, it's a pointy mirror. It gets reflected into the detector, and the other half of the time, because the mirror isn't there, and it goes down the sample pathway, and goes into the detector. That means that we have twice the brightness going through, but only half the time. In this case, we're splitting the beam, so all of the time it's on, going into both detectors. But if we have a low intensity, so in some parts of our spectrum, the light from this general bulb is not very strong, and that means that we've not got very much light intensity. In this case, we save the light intensity. It does cost us time because half of the time it's not going through our sample. We have a different advantage that because we're using the same detector for both paths, then if our detector starts to get dirty, if something starts to wear, if we get something in the way, then it is the same for both the reference and the sample pathway. The only difference really is this mirror and this mirror, which should be identical. That has the big advantage that we can measure down to a much higher absorbance. We can measure a lot lower absorbances with this particular, a lot lower amount of light, with this particular setup. This is way better, but it is more expensive to get it to work, and therefore most sort of normal lab spectrometers have this geometry. But they still have two pathways because there is a lot that we lose on the surfaces of our sample and in this pathway, and we need to take account for the shape of whatever light comes out. It is not the same brightness in every color that we want, so therefore we have to measure the background and our sample all of the time in either type of spectrometer. So for fluorescence, there are some things are a lot easier. Some things are a lot easier and some things are more difficult. So if we take an LED this time, because we are not so worried about the color of light going in. So let's take an LED. We've only got one color of light. Let's have an aperture to make it perfectly collimated. Then we've got a sort of perfect beam. Then we have our sample, and now we have the new problem that because fluorescence isn't very bright compared to our sample beam, and our detector is usually sensitive to both colors, we need to cut out most of that light, and one of the easy ways to do that is to measure our fluorescence at 90 degrees. So if we measure at 90 degrees, most of the light, if we have both beams with an aperture in, most of the light will not get through. It's only light that gets scattered at this point in our sample that will get into our fluorescence sample. Then we will want some kind of diffraction grating that is movable. Grating and our detector. If we want to have a really good device, we would like to change the color of light going in while we're doing that. So we would need to increase our spectrometer by a lot. So if we do that, we would have a xenon bulb or a deuterium light bulb, which give out quite a bit of UV. Then we would need a diffraction grating and an aperture. Let's have a mirror so that it's in the same direction. So let's have grating 1. This would be the excitation, so that we only have one color of light that goes into the sample. So that's our sample. We need somewhere for it to go, so we need something that's black. Black beam dump. Just to collect the light so that it doesn't go anywhere. And at 90 degrees we need a second diffraction grating. Grating 2, diff grating oops, I'm off the bottom here, grating 2, so that we can then measure with our detector what is coming out of our sample. And then we could rotate the first grating to see which colors of light cause our fluorescence best, or we could rotate the second grating to see which colors of light are our fluorescence. It is a bit difficult to measure both, so you usually move one at a time. If we want to measure phosphorescence, we have an advantage that we can wait. Fluorescence, the time scale is so fast that we can't shine the light on, then stop shining the light on and see the fluorescence. But as you saw with my sample, with phosphorescence, we certainly can do that. And so we can have our, let's have an LED lighting it, because it's easier to draw. We don't need a grating on this side if we've got an LED. So an LED lights our sample, and then the light comes out and goes into a detector. Oh, let's have a grating because we want to know what color it is, and then a detector. But if we have a rotating shield with a hole in it, let's rub that bit out so we can have a hole in it, then this is going round and round, rotating shield. Then when it gets round to here, the light can go in, but no light can come out. When it gets down to here, the light can go out, but no light can go in. And obviously we can choose how fast we rotate this to see how long it takes for the light to decay, as well as measuring the color that comes out. So we can also get information on the decay lifetime depending on how fast we rotate this shield, obviously, and how many holes it has in it. Infrared has certain advantages. What we want to see, let me try and get that in frame, what we want to see is the loss of some signal, but it's a lot lower amount of loss than we see in the absorption spectrum, in the ultraviolet visible region. So we have a lot more tolerance, and our source, being a warm bar, is a lot less likely to change in emissivity, and so the brightness of our light will change at a lot lower speed than it will in ultraviolet region. So let's draw it as a resistor. We still need some kind of slit to make it into a beam, or a slit or hole or something to make it into a smaller beam, and we still need a grating in there somehow, but we don't need quite so many components. So if we have infrared and we use a grating to split the light, we will get our sample beam coming through. Let's put our sample in, and this time we're going to go straight into the detector. The detector. We don't need to put the grating before the sample in an infrared because it doesn't matter so much. It's not going to get damaged by the infrared light heating it up. So the grating, the diffraction grating could come here. Grating. This is a fairly old style for a spectrometer because there is a better way of doing it. However, let's write in sample. This is detector. Typically our detector will have to be cooled because we're looking at a very low energy that we're trying to measure, and obviously normal room temperature energy is a bit much, and so we tend to get a lot of noise. So these are often cooled. They're not always cooled, but they're often cooled. Stop. The problem with measuring light one wavelength at a time is that it's very slow because we have to step through every wavelength, and they're not very bright every wavelength, so we're wasting most of our light most of the time. And the more accurately we want to measure it, the worse it gets. So there is a better solution, and it works like this. So we've got our light source, and it goes in to our spectrometer, and it is split with a half silvered mirror into two beams. I've jumped ahead there because I needed to draw it a bit closer to me. It's a little bit uncomfortable, this drawing system. So the light comes in. This is just light coming in. It goes through this half silvered mirror, half of it, hits this real mirror, comes back and goes, some of it, half of it, bounces off again and goes down there. The other half goes back into our source. The bit that goes down here bounces off this mirror, goes back, half of it goes through here to the sample, and the half goes back to the source. So only half of our light goes actually into the sample. However, the interesting part about this is if we have these exactly the same length, every photon of infrared light can get through because it constructively interferes with itself when it gets back to here. However, if it is not quite the same distance, so if we move this one to here, then this path length is shorter by twice the distance than this one, and some frequencies are constructively interfering and some frequencies are destructively interfering. There are relatively many explanations of this on the internet. This is a Michelson interferometer. So what happens now is we get some frequencies that are in phase, particularly bright at this point, and some frequencies that are out of phase, particularly dark at this point. If we now move the mirror, we change the frequencies that we are interested in. So if we draw that in frequency space, I'll just stop and do that. So if we take some frequency and we plot what the intensity with the distance, so the difference in distance of the two mirrors, then at 0 it's always bright. As we go further away till we get half a wavelength away, it's completely dark, so it goes down in intensity till it gets dark. I is for intensity here. As we go further away to exactly one wavelength shifted, it gets to exactly the same brightness again, back to the full brightness, and it goes down and comes back up, and it goes down and comes back up forever. If we have another frequency, then it is the same, just the length of this characteristic distance is changed because the frequency, the wavelength of the light is different. If we plot the intensity of white light, then we get a high intensity at 0 difference between the two paths, and if we move it away, we're losing a small amount of frequencies, but not very many of them. So at any distance very far away, we're losing a few frequencies, but not very many. And as we get closer and closer up, we gather more and more frequencies until we pass through the 0 point again. The lowest amount of energy that we get is quite close to our 0 point, where more and more of the frequencies in our light are in phase. They will never get back into phase again as we move further away, because less and less of the frequencies are the same. They're all shifted compared to each other. This is useful in infrared because the distances are reasonable from a practical point of view. So we can move this mirror by a reasonable amount, smoothly enough and reproducibly enough that in infrared this is possible. If we go to a higher frequency, particularly ultraviolet, this is very difficult to do because moving the mirror would have to be extremely accurate, and any little wobbles in the beam, any little heating up of the instrument would stop it from working. So in infrared this works. In other frequencies it's more difficult. What we're effectively doing is separating the frequencies from each other, but most of them are all coming through at the same time. We now need to deconvolute this is not a spectrum. We now need to extract the data from that, and that is what the Fourier transform does. But this FTIR is Fourier transform infrared spectroscopy, and it is so pervasive, it is so common these days that firstly it is almost impossible to buy a grating type infrared spectrometer anymore, and secondly the technique is called FTIR because the Fourier transform is so much a part of it that it has taken over the whole measurement. What the Fourier transform does is it's a piece of maths that you might have in maths that converts this time spectrum, this type of wave, back into a spectrum. The advantage of Fourier transform infrared is that most of the light is going through and we are measuring multiple frequencies at the same time, and that means that not only is our light brighter and it's on for longer, but we are measuring more frequencies than one at the same time. A common way to improve, ultraviolet visible spectrometers and make them at least smaller, it doesn't make them better but it makes them smaller, would be to measure all of the colors at the same time too, and that's done in the following way. So we've got our light, this will be our light source, we've got our sample, all of the colors are going through the sample in this case, and our detector is then a diffraction grating that splits the light into different colors, and those go onto a linear type of detector, just like you would have in a cell phone camera or sort of mobile phone camera, but instead of being a big chip, it's relatively long compared to its size, so the pixels can be long in this direction, it doesn't really matter, and each pixel is then measuring a different color, and it can then do the same thing as the FTIR in which it's measuring all of the colors at the same time, but the splitting of the light into different colors is not being done by an interferometer, it's being done by a diffraction grating. That does help. I probably ought to put another slit in here because otherwise my beam will be spread a little bit by the sample and then it won't work. So now we can measure UV vis spectra relatively well. The problem of course comes in that our reference can't be at the same time or can't be on the same detector, and so it won't be as high quality as a two-beam spectrometer, but this is a way of getting ultraviolet visible measurements quicker.